This is the first video on section 2.5, the cross product. And I've been saying in other videos that the dot product is a number and the cross product's a vector, but I didn't actually tell you what the cross product is. And so the cross product, we have definition 57 and note 58. Note 58 is a nice handy way to remember how to calculate the cross product. And we do it with a determinant. And if you've ever calculated the determinant of a matrix, this will look familiar. If you haven't calculated the determinant of a matrix, this is still a nice, good visual thing to look at to help you remember the formula. I'm not going to say too much about determinants because this is not a linear algebra class, but you'll learn a lot about determinants when you take linear algebra. But essentially what we do is we look at this grid here. So we have I, J, and K up here. And then we have the components of the first vector in the second row, the components of the second vector in the third row. And we start with the first column. And we ignore the first column and we ignore the row. So we're looking at the I. So we're going to find a number that we multiply with I to get our vector. Remember, every vector in R3 can be written in terms of I, J, and K. So this is going to be the scalar for the I. So we ignore I's row, we ignore I's column. We multiply V2 with W3, and then we subtract V3 minus W2. That gives us the first component of our vector, or another way to look at this is the scalar for the vector I. For J, we ignore J's column, we ignore J's row. And so when we ignore this column, now we have V1 minus W, or V1 multiplied with W3 minus V1, or W1 times V3. So let me say that again. V1 times W3 minus V3 times W1. So we have this subtraction right here. Because it's the second component, we change the sign. So we multiply by -1 of this sum. And then for K, we ignore the row and ignore the column. And we have V1 multiplied with W2 minus V2 multiplied with W1. And that is our third component for our vector here. So remember, dot product is a number, cross product is a vector, and this is the vector. And so we'll do 2 examples in this video before we continue to part 2. So example 59, V is the vector 1, -2, 1, W is the vector -3, 0, 2. We're going to calculate 2 cross products. We're going to calculate the cross product of V with W, and then we'll calculate the cross product of W with V. So we have I, J, and K. We have the components of V, then we have the components of W. And we do our calculation. Ignore I's row, ignore the column. So we have -2 times 2, which is -4, minus 0. And for J, ignore J's row, ignore the column. We have 1 times 2, which is 2, minus -3 times 1. So we have 2 minus -3. Because it's the second component, we change the sign. For K, ignore the row, ignore the column. 1 times 0 minus -3 times -2. So we have 0 minus 6. So our vector is -4, -5, -6. Remember, dot product is a number, cross product is a vector. We take the cross product, W cross V. Same process. So for I, ignore the row, ignore the column, and we have 0 minus -4. For J, ignore the row, ignore the column. We have -3 minus 2 which is -5, but remember with the second component, you change the sign. For k, ignore the row, ignore the column. -3 multiplied with -2 minus 1 multiplied with 0. And so the vector that we get is 4, 5, 6. You'll notice that that's the exact opposite of the vector from part A. And Theorem 61, part 1, tells us that that always happens. That when you switch the order of the cross product, you switch the sign. Some operations in mathematics are commutative. That means that A operated with B and B operated with A are the same. Some operations are not commutative. The cross product is not commutative, as we can see. V cross W and W cross V are two different vectors. However, they are related, as this theorem tells us that V cross W and W cross V will always be opposites no matter what V and W are.